I'm Carol Feghali-Bostwick. I'm a researcher at the University of Pittsburgh, and my research has focused for many, many years on scleroderma. I'm going to talk a little bit about work that in part involves my research, but mostly is also a review of what's known about the environmental factors that are associated with scleroderma. So the title is Nature versus Nurture, and as you know, we're all born with a set of genes that we inherit, but as we go through life, we get exposed to a variety of things in our environment. That could be viral infections, could be compounds, could be pollutants, a variety of things. But what most people don't realize is that what we get exposed to in utero while our mothers are pregnant with us also impacts what happens to us. So what I'd like to go over is what do we know about our genetic background, our genes, and the environment, and what role do these play in scleroderma? So there's a balance. Obviously, we inherit a set of genes for a reason, and we get exposed to a variety of things as we grow up and in our adult lives and throughout life for a reason. But is it an equal balance? Do both our genetic environment, our genetic background, and then the exposures we get play a similar role in development of scleroderma? So there are many things that actually have been reported in the literature to trigger either scleroderma or scleroderma-like illnesses. And we know this because of individual case reports. You know, we've never had an environmental trigger that has caused a large number of scleroderma cases, and that's what it makes it so hard to pinpoint the cause. But we do know of a series of environmental factors that cause a lot of the symptoms that are like scleroderma. Sometimes it's not the full scleroderma spectrum that everybody has, but it's certainly some aspects of it. So for example, silica dust is one of those. You can get exposed to silica in a variety of occupations. In Pittsburgh, it's been known that coal miners, because Pittsburgh is a city that was for years known for coal mining activity, that the coal miners would get exposed to silica dust. And interestingly, it was the wives and daughters that had scleroderma, and I tone it down as Dr. Steen walks in, because she was involved in a lot of those studies. And it was because the coal miners would come home with the silica dust on their clothes, and the wives and the daughters would be cleaning the clothes. And even the coal miners themselves would get exposed, and a lot of them developed a lung fibrosis that's similar to what is seen in scleroderma patients who don't have exposure to the same silica. There's also been reports of exposure to things like trichloroethylene in the dry cleaning business, vinyl chloride, benzene, that have been linked to cases of scleroderma-like illness, epoxy resins, formaldehyde, foam insulation. So a series of them, but again, like I mentioned, none of them were linked to a very large number of cases, making it hard to pinpoint one trigger for scleroderma. There has also been geographical cases, clustering, what we call clusters. You know, someone will say, I live in this town and there's an unusually large number of scleroderma patients in this town, or it gets reported to the CDC. One of these clusters happened actually in London, in close proximity to Heathrow Airport. No one really knows why that is, but you know, jet fuel may be a link, other factors, other chemicals used around airports may be a link. We really don't know. And I'm going to tell you in a little while why it's hard to be able to tell in a definite way that that's a trigger. There have been other clusters, small clusters in Georgia, one near Boston, in the southern Boston area. Has been a small cluster in Indiana, in a town that's sort of surrounded by plastics factories. So these small clusters, again, some have been known by the CDC to occur and others have not, but any additional investigation into these cases has been rather difficult for a lot of reasons. There are drugs that are known to cause scleroderma-like illnesses. Bleomycin is a drug that's given as a chemotherapy for cancer, and it was noticed that after patients get the bleomycin for their cancer, some of them develop lung fibrosis, and actually, due to that observation, we now use bleomycin in mice, in animal models, to trigger lung fibrosis and even skin fibrosis to be able to study things in a mouse model that would be relevant to scleroderma. So the bleomycin model is actually one of the standard models in the lab that's used for studying scleroderma because of this observation of patients getting it, developing lung fibrosis. Cocaine use has been reported in a couple of cases, case reports, to be associated with scleroderma. The difficulty there is a couple of people develop scleroderma because of cocaine use, maybe, but a lot of people use cocaine and don't develop scleroderma. So why is that? There's also been other factors that have been associated with some of the symptoms of scleroderma, such as appetite suppressants that were taken and that people who are taking them develop pulmonary arterial hypertension, which you all know is one of the complications of scleroderma in a subset of the patients. Toxic oil was linked to scleroderma-like illness. That was back in 1981 in Spain, where there was a sale of adulterated oil to in a particular area of Spain, Madrid and surrounding areas, and over 20,000 people were affected. I think it was close to 350 people who died just within the first year, and overall, over 1,000 people actually died. I think the mortality rate was somewhere between 2% and 3%, which is fairly high from just the ingestion of an oil. The symptoms were very similar to symptoms seen in scleroderma, included neuromuscular changes, some skin involvement, some pulmonary hypertension. There's also, I don't know how many of you are old enough to remember this, the eosinophilia myalgia syndrome, which happened when there was a batch of L-tryptophan, which people used to take to help them sleep as a supplement, that was ingested and had a contaminant in it that caused the syndrome in 1989, the eosinophilia myalgia syndrome, that also had scleroderma-like features. And thus the importance of always telling your doctor about which supplements you are taking, even if they are just simple over-the-counter supplements that you can get at any drugstore or any health food store. It's always important to keep your doctor in the loop about the supplements. So what are specifically the symptoms that some of these environmental factors have been shown to cause? So silica dust, as I mentioned, in coal miners and their wives and daughters caused lung fibrosis, and the lung fibrosis was similar to what's seen in scleroderma. It had some of its unique features, but it's still lung fibrosis. Cocaine use also had scleroderma-like lesions. As I mentioned, bleomycin, when given as a chemotherapy, specifically caused lung fibrosis. Vinyl chloride is another interesting one. I don't know whether to point to the right or left. You guys tell me if I'm pointing to the side that's less convenient. But vinyl chloride has caused some of the symptoms of scleroderma, including the skin fibrosis, the lung fibrosis, the Raynaud's, which you all experience. Most patients have this cold sensitivity, and also esophageal problems. And it's interesting because if you take rats and you give them vinyl chloride, you let them ingest vinyl chloride, their skin will actually thicken. So clearly there's a link between vinyl chloride and the ability to cause fibrosis. Trichloroethylene, commonly people in the dry cleaning business would get exposed to that. Also has been shown to cause sclerodactyly and Raynaud's in individuals. Benzene can cause skin fibrosis. Some of the herbicides that are used also can cause scleroderma-like lesions and some lung disease. As I mentioned, the toxic oil syndrome had skin, internal organ involvement, and interestingly, the people who ingested the oil and had the symptoms also had a positive ANA. And I'm sure I don't have to go over what a positive ANA is. Most of you have had that testing, anti-nuclear antibody. It's sort of a generic test as a positive ANA, but there is further testing that can be done to identify the scleroderma-specific antibodies within those anti-nuclear antibodies. And also mercury has been associated with scleroderma-like symptoms, and also with autoantibodies, this particular type of antibody that is known to occur in some scleroderma patients. So let's talk specifically about organ by organ. We've actually narrowed down the list of environmental factors and which organ they are more likely to affect. And so we know, for example, that there are some that specifically are associated with the development of lung fibrosis, so one of the complications of scleroderma. And these are, as I mentioned, the silica dust, the bleomycin drug, vinyl chloride, trichloroethylene, and many of the herbicides that are used in practice. There are others that are associated mostly with pulmonary hypertension, another complication that can occur in scleroderma. These include HIV infection. Actually, HIV patients, HIV-positive patients and patients with AIDS do develop pulmonary arterial hypertension, just like scleroderma patients do. So that's been linked to that. Cocaine use, as I mentioned, some of the appetite suppressants, and I'm sure that's not a complete list of them. But also the Jamaican bush tea, if ingested in fairly large quantities, has been associated with the onset of pulmonary hypertension. But why is it then so difficult? We have all these links, we have all these environmental triggers that we suspect are involved in some of the scleroderma cases. Why is it so difficult for us to say this is definitely the cause of scleroderma? For a variety of reasons. First of all, we know, for example, as an example, that only 5% of individuals who have occupational exposure to vinyl chloride get scleroderma. What about all the other individuals exposed to vinyl chloride who don't get scleroderma? Why don't they get it? So automatically that tells us vinyl chloride doesn't automatically cause scleroderma. It's causing it in a small proportion of people exposed to it. So there must be another factor that plays a role here that protects maybe some people from getting it and makes others more susceptible to getting it. Another example of why we can't say these are definite environmental triggers of scleroderma in everybody is, for example, with the toxic oil syndrome. You know, not everybody who ingested the oil came down with the disease, but interestingly enough, just like in scleroderma, more women came down with the disease than the men, even though both ingested the oil. So why is that? And in a way, these help us get clues into what else could be involved. For example, in the first case, only 5% of workers exposed to vinyl chloride get scleroderma. Why? Well, as I mentioned, maybe there's a genetic susceptibility that makes some people more prone to getting scleroderma if they are exposed to vinyl chloride. Why do we see more women than men getting scleroderma-like features who are exposed to toxic oil? One possibility is that there's a hormonal role. You know, estrogens maybe in women. And actually, we have very recent data from the lab that suggests that estrogen levels are very different in patients with scleroderma from patients who don't have scleroderma or even healthy controls. But also, then why do men get scleroderma? Well, we have some early data that suggests that estrogen, amazingly enough, is very high in men who have scleroderma compared to men who don't. So maybe having high levels of estrogen also makes people more susceptible or more prone to scleroderma, so that when you actually get exposed to one of these triggers, you're more likely to develop the disease. So why is it difficult then for researchers to pinpoint the trigger? Many reasons, because in research, there are certain rules you have to be able to follow and certain conditions that have to apply for us to implicate anything as a trigger of a disease. So first of all, to make something easy to recognize, the disease has to develop as soon as you are exposed to this trigger. And we all know that that may not be the case in scleroderma. Everybody develops it at different times. Sometimes you get Raynaud for years and years and years before you develop other symptoms. Some people get it really quickly. So it doesn't seem to be the same time frame for everybody. There's a lot of variability. Also, to pinpoint a single cause or a single agent as a trigger of a disease, you want to know that there are no other exposures. And that's very difficult. We're exposed to things every single day. Pollution, exhaust from the cars, anything else depending on where you live really and what the pollution level is. Could be something in your work environment, things you get exposed to occupationally. So really it's hard to say I got exposed to only one factor and I got scleroderma exactly 2 years after that exposure, therefore that's the trigger. It's hard to isolate one factor from everything else we get bombarded with basically on a daily basis. Another reason is scientifically to prove something causes a disease, you want to be able to remove that environmental factor and show the disease gets better, which, as we all know, is very difficult to do. And if you remove that environmental factor and the disease gets better, then if you bring that factor back in, the disease starts again. Again, not typical for scleroderma, which makes it very hard to pinpoint. What's hard in scleroderma too is there's a certain latency. You know, we don't know when people get exposed to the triggers and how soon after that the symptoms start. And I'm going to tell you that has become even more difficult with some of the recent research on what we get exposed to in utero that affects what we get. Also, the disease can have atypical symptoms compared to other diseases. You know, every scleroderma patient is different. Everybody gets different complications. Some people never get internal organ complications. So it's not one phenotype that affects everybody. It's more like a family or a subset of a lot of different diseases, and that makes it even more challenging. So let's talk first about the genetics. So genetic changes that may make someone more susceptible to scleroderma can be those that you inherit, you're born with, your DNA, the way it is, the way you're born, and it could be things that are acquired through life. So this is a chromosome, for example. We're all born with a certain number of chromosomes, and what's on our chromosome is our DNA. This is our DNA, the double helix, and for those of you who remember biology, the DNA has 4 simple letters or bases that form DNA: A, T, C, and G. C always pairs with G, and A always pairs with T, and it's those simple 4 that are responsible for the genetic constitution of everybody and responsible for the variability you see in everybody. So that's quite amazing to start off with. But there are many things that can alter that. So we're born with that DNA, but DNA can have mutations introduced into it through life. So these are the acquired changes. And what are things that can change your DNA as you go through life? Well, many things. This is just a very brief list to give you an idea, but some chemicals can cause damage to DNA and introduce mutations in DNA. And by mutations, I mean we can change a stretch of the DNA, or we can take one of these bases, one of these letters, and switch it to another base, and I'll show you what can happen as a result. Radiation, nuclear radiation, can cause changes in the DNA. Ultraviolet radiation could cause changes in the DNA. Some pollutants, some components of food, certainly many drugs, and some pathogens. So some viruses and bacteria that you get infected with sometimes can cause changes in your DNA. And this is what happens, basically. Again, back from a basic review of biology. This is our DNA, and each bar is one of those letters or bases. And our DNA gets what we say transcribed into a messenger RNA. This is what happens inside each cell. Each gene that you have on your DNA gets kind of converted into what we call a message. And the message gets translated into a protein. And what a protein is just a stretch of individual amino acids that get linked together. And then eventually gets folded up and does its function in the cell. So this is how it functions, basically. And what happens is each 3 of these bases, each consecutive 3 of these bases, decide which amino acid is going to be there. So every 3 letters in your DNA correspond to one amino acid. But if you change a single base in your DNA, so you change one letter, you're automatically changing an amino acid. So any change or mutation in your DNA at that point, right here, is going to make your gene generate a different protein product at the end. It's going to generate a different message, and the protein might get folded at the end differently. And anytime you change anything in a protein, you can change its function. So a protein can go from doing something positive in the cell to something negative in the cell, even if you just change one amino acid in it. So that's how critical a single small change in your DNA can be. So is it genes or is it environment? Which one carries more weight then in scleroderma, and how do we determine that? Basically, it could be one of many ways. It could be that your genes and the environment carry equal weight, and they both play an equal role in the development of scleroderma. So what you inherit versus anything you get exposed to, acquired changes, triggers, anything else, that's not inherited. So in this case, we're talking about an environment as anything that's not inherited. It could be that one carries a lot more weight than the other, and it's the predominant cause, or the reverse, okay? One or the other, or equally both. And how do we determine that? Well, the gold standard for determining if your inherited background or the environmental factors play a more important role in the development of any disease is the study of twins. Why? Because we know that twins, especially identical twins, inherit the exact same genetic information from their parents. And if a disease is encoded in their genes that they inherit, then they should both develop it. But if it's something that's not inherited, then identical twins will be discordant for disease. In other words, one will have it and one will not. Does that make sense to everybody? All right. So basically what this tells you is if a disease is dominant, in other words, it's inherited, completely inherited from whatever you get DNA from your parents. Then identical twins, which are called monozygotic twins, from a single egg, one egg splits into two, will have 100% concordance for that disease. Both will have the disease. Whereas fraternal twins that are more like siblings and share half of the genes, half will have it, both will have it, and then half, they won't both have it. If it's a recessive disease, in other words, if you inherit it from one parent, then again, identical twins both will have it, but fewer of the fraternal twins, 25% both will have it. And if it's something that we call multifactorial with mostly an environmental influence, so something that's not purely inherited, but where environmental triggers play an important role, then the majority of the identical twins will both have it, but a very small percentage of the fraternal twins will both have it. Okay, so let's go to scleroderma and take a vote. We did a twin study in scleroderma. How many of you think that our results show it was a genetic disease? Show of hands. 1, 2, 3, 6, 7. Okay, how many think it's environmental disease? All right, let's see who wins at the end. You tell me who's going to win at the end. So we did do a study of twins, and this is the earlier part. Our twin study has grown a lot more since then, and we have a lot more data to analyze, but one thing hasn't changed, and it's the final answer. So just bear with me as I go through it. In other autoimmune diseases, people have done twin studies, and until we did the twin study in scleroderma, there hadn't been one in scleroderma, but they had done them in a variety of other autoimmune and rheumatic diseases. So for example, they had been done in Crohn's disease, and we knew that in identical twins, there was a higher concordance than fraternal twins. In other words, 44% of identical twins with Crohn's disease were such that both twins had it. In fraternal twins, it was 4%. So based on this previous table that I showed you, what does that tell you about Crohn's disease? More, there we go, more identical twins have it than fraternal twins. So multifactorial with environmental influences. If we look at diabetes, similar. You know, the percentages are a little different, but if you see similar, more identical than fraternal, both have it. If we look at multiple sclerosis, again, it varies a lot, but overall more identical than fraternal. If you look at rheumatoid arthritis, another rheumatic disease, more identical twins both have it than fraternal, and the same with lupus. So they all point to these autoimmune diseases and rheumatic diseases as being multifactorial with environmental triggers. So when we started our twin study, we had to see what was out there first before we did our work. Had anybody else done the twin study? And we had found case reports of twins. You know, a variety of people had reported on twins that either both or one had scleroderma. For example, there was one report early on that described one identical, monozygotic, remember, is identical twin pair that was discordant. In other words, one had scleroderma and the other one didn't. But that was only one twin pair, so it wasn't enough to get much information from. There was another study after that that talked about another identical twin pair, but one had scleroderma, one had lupus. So here we are now, two different diseases in a twin pair. After that, there was another one that was described actually in Russia where there was an identical twin pair where both had disease and both had the same autoantibody. I don't know how many of you know your autoantibody status, but we know there are now 9 antibodies that are associated with scleroderma, and each patient usually has a different antibody. Anti-centromere antibody that's listed here is associated with the crest form of scleroderma, the more limited form of scleroderma. And so these twins both had scleroderma, but they both had an anti-centromere antibody, which is interesting. After that, there was another pair where both had scleroderma. One had the systemic form, and one had the systemic form, but known as venous scleroderma, so where someone has internal organ involvement, but without any evident skin fibrosis. After that, there were another, in the literature, we found another 2 pairs of monozygotic identical twins where only one in each pair had the disease. And then another 3 pairs were described by someone else, again, where only one had the disease, and it was mostly limited scleroderma, okay? So not enough to go by. These are not enough numbers to determine the percentage in identical versus fraternal, and there were separate case reports from different countries. So when we decided to do our twin study, we started out with a fairly large group, compared to what was reported in the literature. And we started out by looking, how are they different? Are there any differences? We didn't find any major differences in the form of the disease. In other words, we identified twins who had diffuse systemic involvement. We identified twins who had the limited form of the disease, but we also identified twins that had overlap, scleroderma and overlap with myositis, or scleroderma and overlap with lupus. So the form of the disease didn't change in the twins from what you see in any other scleroderma patient. We then looked at other features of the disease. Were they younger or older than the average patients, or were identical twins any different in age from the fraternal twins we found? And the answer is no, they were similar. Their ages were similar on average. The duration of their disease when they participated during the study were similar on average. And from both the time of diagnosis and also from when their symptoms actually started. So we couldn't find initially any major differences between the identical and fraternal twins that joined our study, but also no major differences from the average scleroderma patients in all the studies. But then we looked at the presence of these anti-nuclear antibodies, the ANA test that you all have had. And what we found was interesting. So this is what's reported in the literature. About 27% of first-degree relatives of scleroderma patients have a positive ANA without having any clinical evidence of any disease, just a positive ANA. When we looked at the fraternal twins, more of the healthy twins of a scleroderma patient, so if you look at twin pairs, one had scleroderma, one didn't, more of those healthy twins had a positive ANA with no evidence of scleroderma. But then when we looked at the identical twins, almost all of the healthy twins had a positive ANA, but no evidence of scleroderma. So what does that mean? That at least the production of antibodies, the ability to make antibodies to have a positive ANA might be genetically influenced, because you have more identicals both having a positive ANA, even though some don't have disease, fewer fraternals, and then even fewer first-degree relatives. So suggesting that the genetic background may play a role in developing a positive ANA. What about other features in the twins? So what we found is even though many of the identical twins of scleroderma patients were healthy, didn't have scleroderma themselves, they had features of what we consider very early or pre-scleroderma. For example, they have abnormal nail fold capillary microscopy. Some of them have this positive ANA that I talked about, and many of them actually had Raynaud's. So not full-blown scleroderma, but certainly some features that we associate with early scleroderma. So at the end, bottom line, in how many pairs of twins did both have scleroderma? Where were concordant for scleroderma? And basically, we found that didn't matter whether you were identical or fraternal. The concordance, or the presence of disease in both pairs of a twin, was very, very low. So as I showed you, in many of the other autoimmune diseases, in identical twins, the concordance for their disease was 20, 30, 40, 50, 60%. And then in the fraternal, it was 5, 10% at most. But if you look at scleroderma in our twin study, concordance in the identical twins was about 4%. Fraternal twins was about 5%. The average was 4%. It was the same, identical, fraternal, and overall it was really, really low, suggesting that the development of scleroderma is not something that's genetically inherited. It's not something that you automatically inherit from your parents, which is good news because it suggests that it's not something you automatically pass on to your children. But there's going to be a caveat to that in a little bit. So good news. If it's not 100% inherited, it's easier to do something about it, okay? And the caveat is this, epigenetic changes. And I'm going to tell you what that is, because that's a new field of research that's pretty much exploded in the past few years, and it's very exciting because it's finally a new lead into a lot of diseases that have been hard to decipher, hard to explain, and this actually makes sense. What are epigenetic changes? Just as the name implies, these are changes on top of the DNA, so above the DNA. And what does that mean? So they occur in addition to the DNA you are inherited. They're known as imprinting. We say a gene is epigenetically changed. It's imprinted. There's an imprint that's made on it, and I'm going to explain what an imprint is. And it was something that was first identified in corn back in 1910. And it wasn't really identified and detected in mammals until 1991. And when you consider research and the scientific field, that's very recent. So what are the epigenetic changes? So this is a lot of technical terminology. I just listed it so you're familiar with the nomenclature if you decide to read up about it online. The one we're going to focus on first is actually methylation. So there are many different kind of changes that can happen on top or above the DNA you inherit. Methylation is right now the more commonly studied one of those. So as I mentioned, you have your DNA, the double helix. It gets transcribed into a message that then leads to a protein formation. And any change that happens at any one of these levels is going to change what happens in your cell and the function of the cell and ultimately what happens to you. So what are these epigenetic changes and how do they affect in this DNA and why can they result in these changes in the function of proteins in your cells? Well, because these changes happened right on top of the bases we talk about. So, we talked about A, C, G, and T as being the 4 codes, the letter codes of the DNA. Well, C, the base, can have methyl groups added to it. So a methyl group can get added, and just for simplification, imagine a methyl group as this little ball is added on top of the DNA. And that happens naturally. We all have what's known as a methylation pattern. We all have different methylation on different parts of our DNA. But the methylation can be changed by a lot of factors. So the methylation occurs on top of the DNA as these methyl groups that attach to these bases. And basically what they do is they can cause some of these areas to open up or to tighten back down. And that's how they alter the functions of your genes. So if the gene is sort of tightened back down, they can turn it off. And if the gene is opened up more, as in this case, it can turn the gene on. So these methylation changes can determine which gene gets turned off and which gene gets turned on in your body. And that makes a lot more sense than having a huge stretch of your DNA change at baseline for scleroderma. Because these methylations can change, and I'm going to show you they change with diet, they change with a lot of things that we all do. And turning on and off genes with these changes makes more sense for a disease that's clearly not inherited based on our twin studies. All right. So imagine, this is your code, right? The DNA code. Remember I said T, G, C, A. And here are the methyl groups, the methylation attached to the Cs. Like I mentioned, it happens mostly on the C. Your DNA, eventually the string of DNA gets wrapped against core proteins. So the DNA is not free-floating like this in the cell. It's actually very compacted, very well folded inside the nucleus of the cell. And it does so by these long strings of DNA being wrapped very tightly around these core proteins, these histones. And what happens is these little dots that are in the methyl groups are on top of the DNA as it gets wrapped. And by being there or not being there, they can open up the DNA more or close it up more. So this is what it practically looks like. So what can cause these methyl groups to change? And thus some genes turn on and some genes turn off. What can do things like that? And this is where you will see that this field is probably going to revolutionize what we do in scleroderma and how we understand scleroderma, because it makes more sense than a lot of the other fields we've looked at in trying to find clues for what causes scleroderma. So in development, in utero, and during childhood, things you get exposed to, even in utero, the mother's diet can change the methyl groups and where they go. Environmental factors like chemicals, drugs, and smoking can change methylation of genes, adding methyl groups, removing methyl groups. Aging, the methylation pattern of your genes changes as you age automatically, and diet can change the methyl groups. So diet and lifestyle. The good news is it makes sense and they're easy to change. We can all modify our diet and lifestyle, right? Those are some of the things that are easier to change. We've had to do them for other things, for atherosclerosis, for diabetes. You have to change your diet, you have to change your lifestyle. So things that are easy to do. So what are the agents that we know scientifically for a fact are linked to changes in methylation or epigenetic changes? Now, I'm not saying these are linked necessarily in scleroderma. I'm just talking about the scientific literature. Do we have evidence that these things in the lab at least can change methylation patterns in methyl groups? And the answer is yes. So we have evidence in the lab that things such as heavy metals, pesticides, diesel exhaust, tobacco smoke, some hydrocarbons, some hormones, including the endocrine disruptors, a lot of things that are in the water as contaminants that mimic the effects of estrogen and seem like estrogen. Radioactivity, some viruses, some bacteria, and many nutrients can actually change the methylation patterns of our DNA and change what genes are turned on and turned off. And scientifically, you can expose cells to many of these factors and show you can turn on genes and turn off others. So what's the bad news then? We already know so much. Well, the bad news is that these epigenetic changes accumulate with age, so you have more and more of them as you get older, but you're exposed to more and more things as you get older, right? You're accumulating all these exposures. And the other piece of bad news is, even though diet, for example, can really affect the methylation patterns of some of your genes, those changes can get carried for generations, and I'm going to show you real examples of that. What is the good news? There's always good news. When I talk, there's always good news. That these can be altered. And I'm going to show you examples of how they get altered. And that brings into the current modern age of research the concept of personalized nutrition. If they can be altered with nutrition, then the nutrition script that you get or the nutrition recommendations will be personalized depending on any disease anybody has. So that's the good news about it. All right, let me give you actual examples of how nutrition can alter epigenetics and can turn on and turn off genes. For bees, so studies have shown that the royal jelly that bees have access to, ingestion of the royal jelly, is ultimately what causes the methylation changes in DNA for a bee to become the queen bee. So it's ingestion of royal jelly that determines queen bee status. So in bees, we know that's a fact. How about in humans? We also know that a pregnant woman's diet, if it's a very poor diet, if a pregnant woman is malnourished, that actually puts the child at much higher risk for cardiovascular disease as an adult. So nutrition of the mother while the baby is in utero can affect the baby's health as an adult. So clear scientific evidence where nutrition, even of the mom, can affect the child. What is another example? So this I'm going to give you extreme. So this study was done actually in Sweden, where they looked at survivors of World War II who basically experienced famine. There wasn't enough food, they were not well nourished, but then they came upon a winter season where there was overabundance of food and they overate. So they went from famine to basically gluttony within a season. And when they followed their children and their grandchildren, they actually found that the people who had been exposed to famine, had experienced famine, and then overate, they found that their children and even their grandchildren ended up with shorter lifespans than people who did not overeat after the famine or who had just normal nutrition throughout. So the methylation changes that were affected by their nutrition was carried through the generations to their grandchildren and affected their grandchildren's lifespan. Another one that's very easy, I think, to understand because many of you have experienced it or know someone who experienced it. So pregnant women take folic acid as a supplement. So the studies have shown in mice that the reason B vitamins are good for pregnant mice is that the studies were done with mice that have what's called the agouti gene. And what this gene, when it's modified epigenetically in mice, does is that the mice will have pups that are both obese and diabetic and have shorter lifespans as a result. But if you give these mice B vitamins in their diet while pregnant, then the pups are normal. They're healthy and normal. And why is that? Because B vitamins are methyl donors. The B vitamins add methyl groups to some of the genes, to the DNA, and that was enough to change pups from being born obese and diabetic to healthy pups. So again, bad news. So we know all this. This is good, right? Nutrition is easy to manipulate. What's the bad news? Bad news then is we already know there are quite a few diseases that are the result of epigenetic changes to DNA. What are these? Prader-Willi syndrome is one of them. Engelmann syndrome. Now, these are not very common, but neither is scleroderma, right? So I'm not talking about massively common diseases, but you'll see there are some that are more common. Beckwith-Wiedemann syndrome is epigenetically determined. Some cancers we now know are epigenetically determined, so changes to the DNA due to these methylation changes. Endometriosis has an epigenetic component. There's some early evidence that lupus also does, and some early evidence that multiple sclerosis does. Good news. The good news is that our drugs are available for reversing these epigenetic changes. The first one was actually approved by the FDA in 2004. It was azacitidine, and it was for the treatment of myelodysplastic syndromes. These are blood disorders that are pretty much pre-leukemia disorders that lead to leukemia within months or a few years, and are treatable with azacitidine because we know they're due to these epigenetic changes, and we know azacitidine reverses those changes to the DNA. And since then, there's been more than 3 actually other epigenetic drugs that have been approved by the FDA, mostly for the treatment of a variety of type of cancers, tumors. So there are drugs in the pipeline that change the methylation pattern, epigenetic pattern of the DNA, can modify it, so it's not too late for it to be modified. Okay. So do epigenetic changes then explain why we don't see scleroderma in both twins in our twin study, why one has scleroderma and the other one doesn't? I think so. I think they do, actually. Other studies in twins with lupus, in twins with multiple sclerosis, have shown that the discordance for disease in the twins can be in part explained by discordance in epigenetic changes. So epigenetic changes barely parallel where the disease happens. So we know that epigenetic changes accumulate with age, right? I told you these changes increase as you get older. But we also know that they accumulate in twins, and that makes the twins a little separate because they accumulate differently in the twins as the twins age. So that may explain why one twin gets scleroderma and one doesn't, right? Their epigenetics are changing with time and becoming more different from each other, whereas the DNA they inherited was exactly the same. We know that the epigenetic differences have been reported in twins with multiple sclerosis and, as I mentioned, lupus. So it would make sense for scleroderma to be similar. We also have done some preliminary work in our twins looking at epigenetic changes, at least on the X chromosome, and we do see clear differences in epigenetics in twins with and without scleroderma. So that may be one of the differences that explains why one person gets scleroderma and one doesn't. So, of course, anytime new observations come into a field, we automatically have a tendency to say, this is the explanation for everything. This is the excuse for everything. So this is still work in progress. There may be a lot more that we don't understand, but it's nice to have a lead into something that makes sense with the pattern of scleroderma that we see, that it's not purely inherited, that it doesn't happen in both twins, that it happens more frequently in adults than in children. And this sort of fits that picture and makes more sense, and certainly a lead worth pursuing as far as I'm concerned. Okay, so let's take a vote now. Who thinks it's mostly genes that are responsible for scleroderma? Who thinks it's mostly environment? I think we swayed everybody towards environment, didn't we? All right, so here's what we think it is. So this is the hypothesis we came up with when we started the twin study, and amazingly enough, it holds true still now. We think that scleroderma is a polygenic disease with multiple exposures. So what we think it is basically is you have a susceptible DNA background. You have susceptibility genes that all they do is make you more prone to scleroderma, but are not enough for you to get scleroderma. That it's environmental things through life that could be acquired changes to your DNA, could be pollutants, could be chemicals, could be diet, could be viral infections, it could be anything that ultimately result in scleroderma developing. And maybe the reason that it's so hard to pinpoint is it could be different triggers causing scleroderma in different patients. And maybe that's why no two scleroderma patients are exactly alike, and that would make a lot of sense. So this is our working hypothesis, is that you have this genetic background, but it's not enough to get scleroderma. And as you get exposed to environmental triggers, so environmental in this case, anything that is not just inherited, you start developing maybe initially Raynaud's. And depending on the trigger, some people may get scleroderma, some people may get something else, lupus, Sjogren's, thyroid disease, primary biliary cirrhosis, any other autoimmune disease. And maybe that might explain why sometimes in families of patients with scleroderma, you see other diseases. Maybe one person has scleroderma, someone else may have rheumatoid arthritis, someone else may have lupus, someone else may have thyroid problems, which is very common in families of patients with scleroderma. So it might be that what you develop and when you develop it and what type of scleroderma you develop is determined by not only what are you exposed to, in what sequence are you exposed to these factors, but when are you exposed to them. What if hypothetically, for example, you get exposed to a chemical, but you're more susceptible to developing scleroderma if you get exposed to that chemical while you have the flu or a bad viral infection, and it takes that combined exposure to develop it. So again, this is just hypothetical, just to give you an example about how complex it is. So this is sort of where we stand with our understanding of scleroderma. There are genetic studies that have been done in scleroderma, and there was one genetic study, the GWAS study, that was led by Maureen Mays in the US and another investigator in Europe, where they joined efforts, which is an admirable thing to do, right? We have a lot more power as researchers when we work together hand in hand to find the answer. And they published this very large genetic study with scleroderma patients, combining a European and American study that showed that there might be a genetic susceptibility to scleroderma or a genetic background that make you more prone, but is not sufficient to trigger the full-blown aspect of scleroderma. So with that, I thank you for your attendance. I hope that I helped not only clarify where we stand on what we think causes scleroderma and what the environment may do to our DNA, but also to give you hope that some of the newer fields and the newer studies we're tackling are ones that lead to very addressable issues that are easy to manipulate via diet or lifestyle or drugs that are becoming available that can change these things. Thank you for your attention. I'd be happy to take questions.